Welcome to this morning's session. I have two announcements. The first is that in terms of opportunities for activities, there's going to be a behind-the-scenes tour of the Cleveland Museum of Natural History. This will happen Monday, that's tomorrow at 2 p.m. The tour is available for up to 14 people. It's no speakers. You get first priority, but you must sign up before the beginning of the afternoon session. So if you're interested, or if you or your companions are interested in seeing the tour, behind the scenes tour at the Natural History Museum, please sign up. More importantly, or at least importantly, at the beginning of the 11 o'clock coffee break, we will have pictures for the symposium. So we encourage everybody to participate. The pictures will be taken on the big wooden stairway that leads down to the atrium. You just exit to the right and go down the stairs. On those stairs, that's where we'll take it. And again, it's herding feral cats to get to everybody. Physicists, yes, that's right. To get you there. So please plan to go there immediately after the start of the coffee break, before you get your coffee. Okay, so today's first speaker is Alain Blondel. Alain earned his first degree in engineering in 1975 and then moved to Orsay to study nuclear physics, culminating in a PhD in 1979. After earning his degree, he's primarily held academic appointments both at CNRS in France and at CERN. Alain describes himself as primarily a neutrino physicist, involved with several, he seems to be involved with numerous experiments on neutrino and particle physics, including serving as co-spokesman for HARP at CERN, as a spokesperson for the mice experiment, and the T2K neutrino experiment. Alain is also working hard on the study of future circular colliders at CERN, especially E plus E minus first step, which will be the main part of his talk today. So please welcome Alain Blondel.
Thank you for the introduction. So yeah, I will talk about the E plus E minus collider mostly. Welcome this morning. So I was preparing this presentation, and I fell on an old lecture I gave in Sweden, but not for the Nobel Prize, of course, which was called From the Z to the Higgs. I thought this was particularly good title for something about the Standard Model 50. The start of my life was very close to the start of the Standard Model, my life as a physicist. I was at the conference on physics of high-energy neutrinos that had been organized to celebrate the discovery of neutral currents, sometimes in the summer of '74. But meanwhile, the J psi and psi prime had been discovered. So I was very impressed by what happened at that conference, especially the summary talk by Sheldon Glashow, which you can recognize very well with his opening of arms. I should be more in the middle, okay. Of course, the neutral currents are here. This is a hadronic neutral current, the real stuff. But Glashow was really great. There was a time where I was hearing the theorists telling me all about rigid trajectories and bootstrap models and so on. And he talked to us about the Standard Model and building the nature with very simple building blocks. He was calling for the search for open charms, so I went to observe 3 neutrino events which looked just like produced by the lambda C. And the Standard Model was born to me and probably also to the experimental world at about that time. That's the lambda and the positron in that old picture. So there was nothing very precise about measurements in neutrino physics until Martin Veltman came to CERN and to SLAC in summer '79 and gave a summer lecture. And he explained that the relationship between the Fermi constant, the weak mixing angle, the Z mass and W mass would be modified by heavy physics if it violates the SU2 symmetry. And that's the case. This is famous rho parameter, the relationship there. And it's modified by loops. Modifications go like the square of the top quark mass divided by W mass. So that was really cool. Electroweak precision measurements are a way to investigate the existence of heavy physics that you cannot see at your accelerators at a given time. I want to make a comment that this is not why the 26.7 circumference LEP was built. Weltham himself, who was part of the committees, insisted that it should be large enough to verify that W pair production was not divergent, which wasn't, but that's not the case of my talk today. The construction of LEP was decided by CERN Council in 1981. I want you to know that between 75 and 81, the world was convinced enough of the standard model that they built a 30-kilometer tunnel without the W being discovered yet. And because it was discovered in 82. Construction started in 83. The big scare of the time was not where the top quark mass was. That was one of the big questions. But the big scare was the number of neutrinos. There was no limit on the number of families. The standard model was built for 2 families. Immediately after it was verified, a 3rd family was discovered, the tau lepton, its neutrino, and the big quark very soon. And that made people scared that there would be an infinite number of them. What would be the consequence of that? That's found in a very nice talk by John Ellis, vintage 1976 here, in a talk that he called Zedology. Now you can Google up Zedology and see what happens. He described all the formula you know and love, in particular this one. The width into fermions is given by this formula, and G Fermi is not as it should multiplied by the rho parameter. Now, all this being said, he explained that this was important because the Z0 peak is large and dramatic as long as there are not too many generations of fermions. It is conceivable that there is be so many fermions as to wash out the Z peak. So if you had many, many generations of neutrinos, the Z peak would disappear. That was scary. Now, of course, LEP was built, and you have the underground. The place where we got in trouble is near Aleph, around here under the mountain. Otherwise, everything went quite well, with 4 experiments on the ring. That's another aerial picture. You don't see those lines when you're on an airplane, but I guess you can guess them. Number of neutrinos was attempted because it's a very important question cosmologically and astrophysically. But before LEP started, the latest paper said 3 is perfectly compatible with the data. The consistency with 4 families still provides a reasonable fit. So we didn't know how many neutrinos there were. Mark II at SLC started having a shot at it. They started in '89. They had 2 papers which were not quite sufficient statistically, but it was coming. I should add that the tau neutrino was an established particle since 1981, so there was no question that the number was at least 3. This is about the tau neutrino. Now, LEP schedule, which I found here in an old slide, is just very impressive. We started some commissioning with 1 weekend of data where we got 8 Zs in August, but then they started serious running the second week of September, and the seminar at CERN for the results was on 14th of October, and there was already a big result. These are very nice events from Aleph, where you see QQ bar events, pair of electrons, pair of muons, pair of taus. That's all you see. You see those. That's everything that you don't see is a neutrino. And those were the results. Now, So you still had to talk by L3, you had to talk by L4, you had to talk by Aleph, you had to talk by Delphi. By the fourth stop, people were already bored of hearing the same thing 4 times. They made fun of it at the famous Theory Christmas party in 1989, where the secretaries were playing the experiments, and they were going around saying, my line shape is the prettiest of all. Here are the results of the various experiments: number of neutrino, number of neutrino, number of neutrino, number of neutrino. If you add the Mach 2 result, the world average was 3.11 plus minus 0.16. That was, there were 3 neutrinos after 3 weeks of running. Okay, Electroweak radiative corrections. And here I have to pay great tribute to Brian, who I think played a big role in organizing this conference, but also in explaining to us how these things work. And great help from Michael Peskin, Robin Stewart, Douglas Kennedy, and this team from SLAM. So you have to, the electroweak radiative corrections are not, as you would think, emission of photons or what. That's kind of trivial. No, it modifies the relations between the main quantities. Everything in the CERN can be calculated from G Fermi, alpha, and mz. Once you have those, then the relationship between other things get modified. And one which was for us particularly important at the beginning was the width is modified by the rho parameter of Veltman. So it is quadratic dependent on the top mass. It also has a logarithmic dependence on the Higgs mass. That doesn't decouple at all either. So from yesterday's talk, Peskin, this would be proportional to alpha times t, and the second one would be proportional to alpha times s. There's others, in particular in the B quark, which are important. In principle, from all these equations, you can disentangle the effects of the top, the Higgs, and even something else. There's enough equations. Now, the Z mass and width are measured using all Z decays. The cross-section is very high, and there's faster statistically, very easy systematically, rather than asymmetries or partial widths that require final state selection. So that's what we did at the beginning. We figured out that the quantity which is sensitive to the number of neutrinos is the peak cross-section. If you draw the prediction for 4 neutrinos, you find that there's less visible cross-section. That if you have 3, obviously, if the Z is produced, there is more invisible stuff, there's less visible stuff. So we measured that, and that's how we got that. The luminosity measurement was the cross-section measurement was a big challenge. Before LEP started, nobody had measured cross-section better than 3%. We paid particular attention to this, down to 1%, and at the end of LEP, it would be measured to 6 × 10⁻⁴. Those quantities, this is the formula that we use. This is theory, the ratio of lepton to neutrino partial width, and it's a very solid piece of theory, while this one are quantities which are all measured at the Z peak. Now, measuring the width now is what would give us the radiative correction that we know and love. The way we did that, the way to do this is to pay attention to beam energy calibration. To do this, we use a technique called resonant depolarization, taking advantage of the fact that the electrons polarize spontaneously in the direction of the magnetic field in the storage ring. It's very slow. You can see the time. This is an experiment where we measure the polarization as a function of time. You can see how slowly it rises from 1 o'clock to 9 o'clock in the morning. Most of the successful shifts were in the night. I remember cooking the onion soup. Massimo Placidi was cooking the pasta. And usually at 9 o'clock, Steve Myers would come in the room and we would lose the beam. However, this one worked out okay. And once you have polarization, you measure the spin precession. So the spins of the electrons precess. The spin precession frequency is a function of the energy divided by, multiplied by g minus 2 divided by the mass, and so it is this quantity here. It's quite straightforward. You have to make a little horizontal field that will kick the spin, and then it precesses, and if you kick at the spin precession frequency, the spin flips completely. And that's what we see here. This is polarization. We kick it, it goes negative. We do it even better here. There's another one which is less polarized, and then we can even pick up the blue one again and come back. The precision was about 10 minus 5. In fact, intrinsic precision is more like 10 minus 6. Now, we would have been very happy if we could do this all the time when taking data, but we couldn't. Not so much because this was impossible, but it was considered too risky to do it at the same time as taking data. The experiments were worried that we would be doing things in their back that they didn't know. So the solenoids were not compensated, and we got a lot of trouble. First trouble is that we made those measurements. You see, if you have to let the beam, you have to, normally you have the luminosity decrease, and we would not have any polarization, and then we would stop the experiments, let the polarization go up, and measure the energy. That means the measurement was not done at the same time as the data taking. So we did the measurements, and the first thing we noticed is that they were not reproducible. The variations were about 3-4 MeV. That was more than we wanted. It wasn't correlated with the temperature. It wasn't correlated with the time of day. What would it be? So there's an old friend called Albert Hofmann who decided that this might be related to the fact that the machine was affected by the moon. At first, we did not quite understand this. My mother always told me that I was a bad boy when the moon was full. And so I thought this was a similar kind of story. Now, what the moon does, it does Earth tides, which are not the same as the ocean tides. They're very much more elastic. They're not resonant process, the elastic process. And indeed, the measurements correlated with the Earth tides. So we decided, that was in 91, we decided to not scan in 92 and spend some time understanding things better. And this is a vintage cartoon, because it was indeed in November 1992 that cartoon came out. And so that was 11 November. We decided that the high tide would be full moon, 11 November 92. And we did the prediction starting at midnight. And that was the measurement. Really pristinely on the slot. You notice that Steve Meyer did indeed come in the room at 8 o'clock. He went back for lunch and out for dinner. Of course, this was only the beginning. When we did those measurements again and again, we realized that this was the day from the start of the run in March. And the average just shifted enormously. Now, my wife was working at the time on the ecology of the lake. So I went to see her friends. She wouldn't give me the data, but her friends would. And they said, this is the level of the lake. Didn't look like much. But I dropped the slide. This was plastic at the time, and you could drop it. And when I put it back on the screen, it was looking like this. And that was really correlated. So the energy depended straightforwardly on the level of Lake Geneva. Okay, they take the level down because they use the electricity during the early spring before the snow melts, and then when the snow melts, the lake goes back up. That's when we take the data and it shifts. Okay, so we had some success in the press with this moon story, because they mostly French, but quite a few. The lady who was running the science show had exactly the same reaction as my mother. She thought we were bad, not the accelerator. Anyway, in '93, the Z-peak was scanned. We were happy enough. We scanned thoroughly the Z-peak with a sequence of data points at the half-integer spin tunes, 101.5, 103.5, 105.5, which are called peak -2, peak, and peak +2. So it's a beautiful place, away from spin resonance, and very nearly optimal for the Z-width determination. At the same time, the muon forward backward asymmetries, which depend strongly on energy, were measured, as well as tau polarization and all the possible things that measure sin square theta effective. At the end of the year, the cross-section and asymmetry data were analyzed and put together by the LAP Electroweak working group to obtain a prediction of the top quark itself. We did not do this experiment by experiment. We sent all the data blindly to the fit, and they did the fit, and they come out with a result. And mind you, this was March 1994. That was given by Bolek Pichik at the Electroweak 94. 177 plus minus 11, that's the statistics from the data errors, plus minus this much if you change from the central value of 100 GeV to 1,000 GeV or to 30 GeV. So 1 month later, CDF produced a paper where they quoted that result, and they reported an excess of 2.8 sigma in the same mass range with a best value of 176.16. So that was really very fun for us. We worked on these things, had our nose into the tides and all these troubles, and our paper was actually quoted less than a month after being produced. So that was really, really fun. This is the history of the predictions and the direct limits and the direct measurements of top mass. You've seen that very, very many times. CDF and D0 went on to discover the top quark in 1995 with 5 sigma each. LEP and SLC went on to predicting the Higgs mass using the top quark mass from the tevatron. Once you had that mass, the only thing you didn't know was the Higgs boson mass. Well, that wasn't the end of the troubles with the energy, because we realized that there were other things happening. We took data continuously. We made a model of the variation of energy with temperature, tides, etc. We kept taking the data, and lo and behold, that was the prediction, and we saw a deviation. It was less deviation than before, but it was a deviation. It took some time to understand what was happening. There was no effect on the width, but there was an effect on the mass, potentially, because you calibrate your energy up there, and you extrapolate back with this model, you're going to make part of the data an error. That's the problem. But the error is always in the same direction, apparently. We put NMRs in the magnets of the ring, and we found this. This is what the NMRs were saying. They were not only going up when you kept the current on the magnet, but they were going quiet between midnight and 5 o'clock in the morning. Who is going quiet between midnight and 5 o'clock in the morning? That must be people. So this is a clear sign of human activity, except physicists, of course. So what was happening? And we understood that this was due to the train company. The train company does not operate trains between midnight and 5 o'clock. It does not operate trains on strike days, and this is how we found out. Because there was a day I found myself stuck in Paris by the train strike, and when we got this Swiss engineer to give us the paper, a paper with little holes, that was the data recorded of the voltage between the ground and the tracks, we found that it was flat on that day. So all these things can be, of course, measured. It would none of this would have happened if we took data at the same time as the calibration, of course. So we understood that there was a kick in the ground. When the train passed by here, it was sending its voltage flow to the underground, where it would just follow the ring of LEP around and come out again when it goes close to the river here. That is very well measured. We completely understood that problem. Okay, so at the end we finally made a good model of the ring, which is very nicely reproduced. The model reproduces the measurements we made. Well, that was too late. That was in 99. We'd finished. We were hunting for the Higgs at that time. We couldn't remeasure the Z mass and width. Anyway, the last results of LEP and SLC and Tevatron were published in 2005. There's still results coming out of Tevatron on the top mass, on the forward-backward asymmetries of the Z, but they were not included in this. And at that time, in that paper, you find the Higgs boson mass, 129 plus 74 minus 69. Now, the following year, this is a log. You're measuring a log, so the result fluctuates a lot, depending on the input. Okay, so that was the plot that was given. This is famous agreement of the standard model with all these precision measurements. You can find that this is beautifully normally distributed. Out of 20 measurements, there's 13 or so which are within 1 sigma, the rest below 2 sigma, and just 1 out. And it happens to be the B quark asymmetry, which nobody likes, but that's not their fault. The next big step. Time is it? Okay, I have a bit of time, that's good. So, in that period, the top mass was predicted, mostly from Z mass and width. The top quark was discovered at the Tevatron, and Toft and Wertmann got the Nobel Prize. You have to get used to this when you're an experimenter in big experiments. Then, 97, 2013, the Higgs boson mass was cornered from the LEP, Electroweak fits, from the Tevatron top mass, from the W mass. The Higgs boson was discovered, Engler and Higgs got the Nobel Prize. The standard model appears to be complete, with the notable exception of the right-handed neutrinos, of course. Furthermore, the mass of the top and the mass of the Higgs happen to be in a place which is slightly uncomfortable, but perfectly sufficient for us to have survived since the Big Bang, and probably for another couple universe lives further. So we're happy with that result. What this plot says is that there's no, from this point of view of stability of gravitation, there's no need for anything else than the particles we already know. And in fact, you better not put anything else that troubles this particular prediction. So we must continue. The particle physics doesn't stop with this particular result, of course, because we know that there's dark matter in the universe. We know that there's a baryon asymmetry, so we need something that violates CP and transforms particles in antiparticles in some way. And you need also something that gives neutrinos a mass, because the standard model has more than one way of doing it. So how do we proceed? There is no particular indication of where the sources of explanation for the neutrino masses or dark matter is. This can be anywhere between milli-electron volts and zeta electron volts. So we need to do a very broad brush search. This is what we have found to be the wider search we can do with accelerators at this point of time. So we are discussing building a new ring around Geneva. So Geneva is here, in fact, inside. By construction, it should be connected to the CERN complex. By contraction, it should avoid going under mountains. And so there's just about the right amount of space here. avoiding this mountain, the Alps, the pre-Alps, the Jura, and this little thing here, and going under the lake, which is the least of our problems. You're laughing, but the lake doesn't leak. If the lake leaked, there would be no lake. So the study is of a 100-kilometer infrastructure, which would fit, and which is designed in such a way that you can put a 100 TeV proton collider in it. There was lots of problems putting the LHC in the LEP tunnel. They don't want this to happen again. So there's two possible, you can't do this in one go, so you have two possible first steps. You can either build an E plus E minus collider in that ring and do another LEP, except that this time you're going to be able to do the Higgs on the top properly, or you can increase the energy of the LHC inside the LEP tunnel from 16, with 16 Tesla magnets, hoping to reach 28 TeV. So European strategy wants an ambitious post-LHC accelerator project, and that's the best incarnation of that. From what we know today, the FCCE is probably the fastest and cheapest way to 100 TeV, and that combination also produces the most physics. So that's the assumption I follow in the rest of this talk. That's also the one I like best. It turns out to be not bad start for muon collider as well, so we're covered for the very high lepton energies. FCCE, so this is an electron-positron collider. Thanks to the very large ring, the synchrotron radiation goes down, so you can reach, instead of 200 GeV, you can go to 380 GeV, or even 500 if you really wanted to. And we get huge luminosities at the Z and W using the B factory techniques. So instead of having 10 to the 31 luminosity at the Z, we get 4 10 to the 36. Instead of having 10 to the 32 luminosity at the top at the Z 200 Hz threshold, top maximum cross section, we get somewhere between 1.6 10 to the 35 per square centimeter per second. So that's about a factor of 10 more than the linear collider project. So this is the statistics we're looking at. 5 10 to the 12 Z's, 10 to the 8 pairs of W's, 10 to the 6 ZH, and 10 to the 6 TT bars, with center of mass energy errors which we want to push down to these levels. Implementation, we're going to go just like the lab, start with the Z, W's, ZH threshold, TT bar threshold, TT, and the top energy. The discovery potential, at first we just thought we're going to do the Higgs boson. But then you realize that the Z factory and all the precision electroweak measurement has an enormous discovery potential, because the precisions are really 20 to 50 times better than we had at lab. And that's equivalent to square root of that in energy range. So it matches the increase in energy that you'll get later with the Hadron Collider. There's also an enormous amount of flavor physics. 5 10 to the 12 Z decays will give you 10 to the 12 BB bar events, or 2 10 to the 11 taus, where you can even get signs of right-handed neutrino flavor violations and so on. Dark matter has invisible decay heats of Z, and very, very weakly particles such as right-handed neutrinos. If I have any sort of time or questions, I may get into a little bit of right-handed neutrinos. And finally, you get QCD in its great beauty. In particular, the Higgs has an 8% decay into gluon, and we will have a very pristine sample of pure Higgs tagged with the Z decay. So the Higgs is a very important aspect, but it's not the only one. All the rest is extremely powerful. So we put out the first paper in 2014. My slides from a month ago had 398 quotes. We got 418. What's interesting here is that the kind of papers that are interested in this machine is not just Higgs. There's a lot of different things. So this is a table. I'm not going to go through it. We looked at whatever we did at LEP, and typically we increase by a factor of 20 to 50, probably. Probably the smart guys in 20 years will do much better. That's the EFTs that Michael Peskin showed yesterday. In green, what you do with the Higgs. In red, what you do with the Electroweak precision measurements. And you can see that they're very much orthogonal in the sense that there's many things you do with the Higgs, and even more many things you do with Electroweak precision measurements, and they go higher in limits. The theoretical uncertainties in the calculations are, at present, biting out your capabilities, but our theorists have promised that if they are given money, they will do the calculations. Hadron Collider, 100 TeV, it's just a big LHC, okay? It's the highest center of mass energy, so you can go up to 30 TeV, search for direct productions of particles. Final word on natural supersymmetry. I'm not sure you'll believe me on that. I must have said this 3 times before in my life. Huge production rates for Higgses, W's, and Z's. So the Higgs precision test for the TTH, the triple Higgs coupling, the gamma gamma mu mu, all these things which are rare decays, which the electron machine has a hard time reaching at. Search for invisibles, etc. And very clean signals at high PT physics. The difference with the LHC is that high PT gives you a lot of new things. Complementarity is enormous. I'm really stable for the Higgs couplings. You see the couplings measured by the FCCEE. You see a gap in FCCEE immediately. You see the Hadron Collider pitch in. The triple Higgs coupling, we can measure at 30%. The Hadron Collider can go down to 3%, etc. So, for the FCC, the design study is establishing the feasibility or the path to feasibility of an ambitious set of colliders after LEP and LHC at the cutting edge of the knowledge and technology. I have not discussed the right-handed neutrino search, but I can answer questions. Both FCC and FCCHH have outstanding physics cases, each in their own right. And the sequential implementation maximizes the physics reach and also maximizes the feasibility. So we got a good program for the next 50 years. Thank you.
Can you tell me, for instance, for LED, as you said, you had the number of neutrinos that it could clear, right? For the case for LED. Plus, it was other times. Can you tell me one measurement that FCCE will do that no other of the E plus E minus plants will do, plant machines in the world will do, and which is very relevant? Something that you call the attention, because when one quotes many items,
I got many items. There's one,
yeah,
which is simple to understand. If you have 5 × 10⁻⁴ Z's, you're going to prove, because the branching ratio into neutrinos is 20%. That is 2 each, so it's 40% of the number of Z's. So you're going to have 2 × 10⁻12 neutrinos. If you have a heavy neutrino which is below the Z mass, that's 50 GeV, say, and the light neutrino is 50 milli-electron volts, the mixing angle is 10⁻12. With 2 × 10⁻12 Z's, you're going to see 2 of them. They happen to decay in the detector.
When you say that is the missing angle, you're assuming Taiwan,
Type 1 seesaw, the most straightforward, simple thing. Okay, I'm not a good theorist. I cannot think of all the possible things.
So Taiwan. So
I'm just concentrating on the plausible things.
I'm trying to understand. With Taiwan, you cannot see lepton number violating signal, but you can see just the case. How are you going to distinguish? And yes, okay.
Okay, so that's a little joke again. So the right-handed neutrinos have several things which happen. Not only they can be produced directly, they can also be produced, for instance, they can also be not produced in muon decay. And so they change the value of G Fermi with respect to what you think it is. That's a very particular set of violations of the standard model relations. You can also have the same thing in tau decays, etc. It would be interesting to measure G Fermi for the taus. And there's a whole thing which is called effect on precision measurements. You can produce them from Z decays, or you can produce them from W decays. Now, W decay is particularly nice because you know you can tag the lepton flavor at the beginning and the lepton flavor at the end. So you can see if it's charge conserving or not, and flavor conserving also. So at the Z, it's particularly easy to see. This is a right-handed neutrino that decays into a FCCE detector. Okay, it's in the middle, and you got a lepton in it. That's what we can investigate. We're working hard on trying to see if the hadron machine cannot get into that region. And so, right. So that's what, if you have the hadron collider able to do this, and I think that's where having the lepton collider first would be very helpful, because this is a very special trigger. Okay, the LHC experiments today are not able to trigger on these things. You can even see those oscillations now between, like sign, opposite sign, etc. So that's a nice paper by Stéphane Antouche. That's a very particular set of parameters, but that's just for see what you could do. So that's what we do. That's the electron machine coverage. This is the electron machine coverage by precision measurements. This is the hadron collider coverage, and even the EP collider, because here you get leptons in the initial state and a neutrino in the final state. So every charge current event can produce a heavy right-handed neutrino.
Some of these things require more hypothesis, but fair enough. What about Japanese friends?
Japanese friends. You take those numbers. How many Z's can you do at the IRC? Factor 1,000 less. So you bring those numbers up by a factor 1,000. These numbers, I don't know, precision measurements, I think that's also, you're changing paradigm. You go from a Z mass measured at 2 MeV to a Z mass produced at 100 keV.
Okay, great, thanks. I think we'll have to end there. Can we break that one again? Great talk.